My name is Vedran Bobanac. I come from University of Zagreb, Faculty of Electrical Engineering and Computing, and I'm currently with the Department of Energy and Power Systems. So you can see the title of my presentation, it's about lithium-ion batteries. So we all know lithium-ion batteries are very big right now. They're growing, they'll continue to grow in the upcoming period. So when talking about battery modeling, we can distinguish between detailed low-level models for describing chemical properties and also high-level models of electrical properties which are aimed for inclusion in higher-level optimization models. And we are interested in the second. So shortcomings of a lot of these models are that they disregard nonlinear battery charging characteristics and also that they inadequately count for battery efficiency, be it completely disregarding the efficiency or disregarding its variability. So the outline of this work, we did some experiments related to lithium-ion battery efficiency. The results can be used to potentially improve a variety of battery models, algorithms for state of charge estimation, as well as process of sizing and scheduling battery energy storage. So we did some experiments, so we need experimental setup. We use this professional bidirectional grid-tied converter for charging and discharging batteries. So battery testing is tiresome and long process because it takes a lot of time to charge, discharge batteries and to repeat these cycles. So we developed our own software in LabVIEW from National Instruments, and we use this software to control the converter. And in this software we can set a bunch of parameters for charging, discharging, and for arbitrary number of cycles, and just leave it to run for days. And then when it's finished, we just come pick up the logs and process them. And in this work, we tested two commercial battery cells, two technologies which are very popular: lithium nickel manganese cobalt oxide and lithium iron phosphate. Now I want to talk a little bit about battery efficiency. First division is by electrical quantities, so it can be Coulombic efficiency related to amp hours that enter or exit the battery, Voltaic efficiency, terminal voltage, different terminal voltage of the battery during charging and discharging, and energy efficiency, which is a combination of the two. Also, the other division is by energy flow. So efficiency, we can regard it as one way, so either during charging or during discharging, or round-trip efficiency during the whole charging-discharging cycle. The trick here is that we have to observe the same state of charge range during charging and discharging. Because, for instance, if we fully charge the battery and only partially discharge it, the obtained round-trip efficiency is not really valid. So here we can see, I'll just move here a little bit. So this energy charging, when we charge the battery, we take some energy from the grid. And we have some losses during charging process. Only portion of this energy gets actually stored in the battery. When we discharge the battery, we use this energy that was stored. Again, we have some losses, and we deliver some energy to the consumer. So this energy here and this energy here is easily measured by measuring battery terminal voltage and current. And we can calculate round-trip efficiency from these two values. However, this energy that's actually stored in a battery, it's not so easily measured. So in order to do so, we need to apply some technique. So one way of doing that is employing open circuit voltage characteristic. So we did a number of tests. Firstly, we cycled the battery with low rates to obtain this OCV characteristic, and then we cycled the battery with different charging-discharging rates in both constant current, constant voltage, as well as constant power, constant voltage cycles. So these are the results. In the middle, the dotted line is open circuit voltage characteristic, and we see also different voltages for different charging-discharging rates. So the two technologies are compared, results are similar. So for higher charging rates, we have higher voltages. For higher discharging rates, we have lower voltages. And this kind of voltage hysteresis is actually the main cause of energy losses. So, Coulombic losses for lithium-ion batteries are Coulombic efficiency is pretty high for lithium-ion batteries, around 99%. This is well known, documented in papers and literature, and we proved it also here in our paper. But these voltaic losses is what causes energy losses. We see that characteristics are different. NMC technology has steeper rise of voltage and then a longer constant voltage phase, especially for higher rates, where LFP technology has a flatter voltage curves and then very short constant voltage phase towards the end of full charge. So what we did now, we took these characteristics and we calculated sample-wise ratios of charging and discharging voltages on one side and open circuit voltage on the other side. And the results are here. We display only constant current mode and constant power mode, since in these modes rates are constant. Constant voltage mode, rates drop, so we don't show them here. The results are similar, so we'll concentrate on the left graph. The upper one is charging, the lower one is discharging, and the two technologies are compared. We can see that curves are non-linear, however, they can be considered constant in a relatively wide SOC range. And we can also see that for higher rates, efficiencies drop for both charging and discharging, and LFP technology has generally higher efficiencies than NMC technology. So this graph here kind of sums up the whole paper. We have constant current charge and discharge, as well as constant power charge and discharge, and both technologies are compared. So the first two, the purple and red bars, are for voltaic and energy efficiency of NMC cell, while cyan and blue colors are for voltaic and energy efficiency of LFP cell. So main takeaway here is that voltaic and energy efficiencies are almost the same. So what we can do, instead of calculating power integrals, we can simply take measured voltage, take the mean values, and calculate ratios with the open circuit, with the mean value of the open circuit voltage for the observed SOC range. And by doing so, we can obtain one-way voltaic efficiencies which are representative of one-way energy efficiencies. Also, what's pretty clear from here that LFP technology, again, what we said before, has higher values of efficiencies. And that brings us to the conclusion. For lithium-ion batteries, almost all energy losses are caused by voltaic losses. This is expected for lithium-ion batteries. And we also show that one-way energy efficiency, which showed it in the previous slide, can be calculated simply as one-way voltaic efficiencies. And we won't be making much mistakes. So this is true for lithium-ion batteries. From some other, this may not be the case. LFP technology, LFP tested cell generally has higher efficiency than the tested NMC cell. Charging efficiency showed that to be generally higher than the discharging efficiency by a small margin. Of course, this has to be observed for the same charging-discharging rate. Because if you have high charging efficiency, high charging rate, low discharging rate, then of course they will not be, the difference will be much bigger. There is no significant difference between cycling the batteries in constant current and constant power modes. And we also show that voltaic efficiency curves are nonlinear, but they plateau in relatively wide state of charge range, roughly 10 to 90% for LFP technology and 20 to 100 for the tested NMC cell. So by operating batteries in these ranges, we can reduce energy losses. And with this, I conclude my presentation. And thank you
for your presentation. So, any questions from the audience? No? Okay, so let me ask you a question myself. So, how do you get a single value for the voltaic efficiency? Are you averaging the flat part? Or?
Well, yeah, we took just this constant current and constant power modes. We didn't take just the flat part, we did the whole part. The whole curve here.
So it's an average of all the
Yeah,
curves.
it's the average of these curves. Yeah.
So when you have curves where at the edges it's
they go down, yeah, it's not the same as in this constant, but it's pretty similar because here we don't go all the way to zero here on the y-axis.
Sure.
It's 0.8,
Okay.
so it's pretty close. Yeah, it's a little bit different, but yeah, it can be described by a single number roughly.
All right. Okay. Thanks for that.
You're welcome.